A silver ship vanishes into a swirling vortex of stretched starlight. You have just glimpsed one of science fiction's most iconic ideas. But what if the reality is even stranger? We are about to journey through 50 incredible theories about wormholes and the mind-bending potential of space-time travel itself. By the end, you will see the fabric of the universe in a completely new light. We will explore if a black hole could secretly be a tunnel and whether time travel would unravel reality itself. What single cosmic mystery do you hope these theories might finally solve? The elegant equations of general relativity hold a secret passage. Albert Einstein and his colleague Nathan Rosen first uncovered this cosmic shortcut not in a flash of inspiration, but through the cold, hard logic of mathematics. Their work described a gravitational monster so extreme, a black hole, but hidden within its heart was a tunnel. They called it a bridge, a structure linking two separate points in the fabric of space and time. Picture the universe as a vast sheet of paper. A wormhole is like folding that paper so two distant dots touch, creating a bridge that bypasses the long, straight line between them. This was the birth of the Einstein-Rosen bridge, the very first scientific theory of a wormhole. Yet this initial model had a fatal flaw. The bridge was terrifyingly fragile. The moment it formed, the immense gravitational forces at its core would cause it to pinch shut, collapsing instantaneously. Not even a single photon of light could make the journey before the tunnel slammed closed, trapping anything inside forever. This brilliant idea was, in its original form, a door that locked the moment it was opened. That cosmic door may slam shut, but what if we could build a door frame strong enough to hold it open? This was the revolutionary question posed by physicists like Kip Thorne, transforming the wormhole from a mathematical curiosity into a potential gateway. The key to a stable, traversable wormhole lies not in the structure itself, but in what you line it with. It requires something known as exotic matter. This is not just a rare material, it is a substance with a truly bizarre property, negative energy density. Think of gravity as a force that always pulls, always attracts. Normal matter, the stuff that makes up our world, reinforces this pull, but exotic matter would do the opposite. It would exert a kind of negative pressure, a repulsive gravitational force. To visualize this, picture the throat of the wormhole as a tunnel desperately trying to crush itself shut under its own immense weight. Now imagine lining that tunnel with a material that actively pushes outward, a cosmic scaffolding that counteracts gravity's relentless squeeze. This exotic matter would act as the ultimate support beam, propping the wormhole's throat open long enough for someone or something to journey through. The challenge, of course, is staggering. We have no confirmed natural source of exotic matter. Creating it, even in microscopic quantities, would demand technology and energy far beyond our current grasp. So while the theory offers a breathtaking blueprint for a stable wormhole, the very ingredient needed to build it remains one of the universe's most tantalizing and elusive secrets. Building a stable wormhole is one thing, but using it as a time machine is an entirely different cosmic proposition. The very structure of a traversable wormhole might be the universe's ultimate time travel device. This idea comes from a powerful consequence of Einstein's special relativity, the same theory that gives us the famous equation E=mc². One of its core principles is time dilation, which states that time does not pass at the same rate for everyone. If you were to take a journey at a significant fraction of the speed of light and then return to Earth, you would find that less time has passed for you than for everyone you left behind. Now apply this to our wormhole. Picture a stable wormhole with two mouths, mouth A and mouth B, initially synchronized in time. What if we could take mouth B and send it on a high-speed journey to a distant star and back while mouth A remains stationary? Due to time dilation, mouth B would experience less passage of time. When the journey is complete and the two mouths are brought back together, they would no longer be synchronized. If only 1 year passed for mouth B, but 10 years passed for the stationary mouth A, then stepping into mouth B would send you 10 years into the past of the location connected to mouth A. This creates a closed time-like curve, a path through space-time that loops back onto its own past. The implications are as dizzying as they are dangerous. This scenario immediately invites the classic grandfather paradox. What would happen if you traveled back through the wormhole and prevented your own grandfather from meeting your grandmother? The logical contradiction seems to unravel causality itself. If you were never born, how could you have traveled back in time to set these events in motion? This paradox is not just a plot device for science fiction. It is a serious problem that physicists grapple with, forcing us to question whether the laws of physics have some hidden mechanism to prevent such violations of cause and effect. The paradox of traveling to a past you can change seems to forbid such journeys, yet the quantum world operates on a different set of rules entirely. Here, the theoretical need for exotic matter finds a whisper of validation in a real, measurable phenomenon known as the Casimir effect. In a stunning laboratory demonstration, two uncharged metal plates placed incredibly close together in a vacuum will experience a faint but undeniable force pulling them together. This happens because the empty space between the plates is not truly empty. It is a seething sea of virtual particles that constantly flicker in and out of existence. The plates restrict the kinds of quantum fluctuations that can appear in the narrow gap, meaning more virtual particles push on the plates from the outside than from the inside. The result is a tiny region of space with a negative energy density, exactly the bizarre property required to prop open a wormhole. For a fleeting moment in that microscopic gap, we create the very stuff of cosmic shortcuts. This leads to a profound speculation. If this exotic quantum energy exists between two metal plates in a lab, could it be a clue that space-time itself is riddled with similar structures on a subatomic scale? Perhaps the fabric of the universe is not smooth but foamy, teeming with countless miniature wormholes that form and collapse in an instant, too small for any particle of matter to traverse. We may be walking through a hidden network of cosmic tunnels every single day, completely unaware of the intricate architecture woven into the foundation of reality itself. Perhaps the universe itself provided the first wormholes. Instead of requiring a futuristic civilization to build them, these cosmic shortcuts could be ancient relics woven into existence in the chaotic first moments after the Big Bang. During that primordial fireball, the entire universe was compressed into an inconceivably hot, dense state. In such extreme conditions, the very fabric of space-time would have been turbulent and unstable, fluctuating wildly. It is within this frothing cauldron of reality that physicists speculate wormholes could have spontaneously formed. The immense energies present could have twisted space-time into knots, creating tunnels that linked one fluctuating region to another. These would be primordial wormholes born not from engineering but from the raw, untamed physics of creation. The question then becomes, what happened to them? As the universe expanded and cooled at a fantastic rate, most of these nascent tunnels would have been stretched, pinched off, or collapsed instantly. But what if a few of them, through some random fluctuation or a lucky alignment, managed to survive the rapid inflation? They could still be out there today, hidden threads stitching the cosmos together. This theory offers a compelling solution to a modern mystery. If such a wormhole persisted, it could connect two regions of space that are now astronomically far apart. A journey through one of these ancient gateways could, in theory, allow you to step across billions of light years in an instant. This means the universe might already be equipped with a ready-made transportation network, a web of cosmic shortcuts left over from its explosive birth. The challenge, of course, is finding one. These primordial passages could be lurking anywhere, their entrances perhaps disguised as mundane black holes or simply lost in the vast darkness between galaxies. Einstein famously called quantum entanglement spooky action at a distance, a phenomenon so bizarre it seems to defy the speed of light. Two particles can become linked or entangled, such that measuring the state of one instantly influences the other, no matter how far apart they are. For decades, this was viewed as a ghostly connection, a purely mathematical correlation with no physical bridge. But a revolutionary idea suggests there might be a tangible tunnel behind the magic. This is the ER equals EPR conjecture, a proposal by physicists like Juan Maldaisner and Leonard Susskind. The name itself is a key. ER stands for the Einstein-Rosen bridge, our familiar wormhole. EPR stands for Einstein, Podolsky, and Rosen, the physicists who first highlighted the strange implications of quantum entanglement. The conjecture boldly states that these two concepts, one from general relativity and one from quantum mechanics, are not just analogous, they are one and the same. An entangled pair of particles, in this view, are not mysteriously communicating. They are physically connected by a microscopic wormhole. This wormhole is not a tunnel through ordinary space you could ever travel through. It is a bridge in the deeper geometry of space-time itself, a structure so tiny and transient it only manifests as this instantaneous correlation. Think of two dancers on opposite sides of a vast, dark stage. To the audience, their perfectly mirrored movements seem like magic, a spooky connection. But what if there is an invisible thread, a tiny, unseen wire linking their hands? The dancers are the entangled particles, and the wire is the wormhole. This idea is so powerful because it forges a potential peace treaty between two warring pillars of physics. General relativity describes the universe on the largest scales, the force of gravity and the curvature of space-time. Quantum mechanics describes the universe on the smallest scales, the behavior of particles and forces. The two theories have been notoriously difficult to reconcile. But if every instance of quantum entanglement is secretly a tiny wormhole, then the spookiness of the quantum world finds a beautiful explanation in the warped geometry of general relativity. The fabric of space-time itself may be woven from an unimaginably dense fabric of these quantum threads, a hidden network of connections that binds the universe together from within. If every black hole is a point of no return, what lies on the other side of that terrifying threshold? The mathematics of general relativity offers a stunningly symmetrical answer, a white hole. This is the theoretical opposite of a black hole, where a black hole's event horizon is a one-way membrane trapping everything that crosses it. A white hole's horizon would be an absolute exit door. Nothing could ever enter a white hole from the outside, but matter and energy could potentially be violently expelled from within. The equations suggest a perfect connection, a wormhole linking the infinite gravitational well of a black hole to the erupting fountain of a white hole. Falling into the black hole in one part of the universe could, in this elegant model, mean being spewed out of the white hole in another. It is a cosmic recycling system written into the very fabric of space-time. Yet for all its mathematical beauty, the white hole faces a profound physical problem, the second law of thermodynamics. This fundamental law states that the universe as a whole moves from order to disorder, a property called entropy that always increases. A white hole, by its very nature, seems to reverse this process. It would be an object of incredibly low entropy, a perfectly ordered state that spontaneously generates and ejects matter without any apparent input of energy. Most physicists view this as a powerful argument against their natural existence. While black holes are observed and confirmed throughout the cosmos, not a single white hole candidate has ever been found. They may simply be mathematical ghosts, beautiful solutions to Einstein's equations that the universe, in its messy reality, chose not to build. Their enduring appeal, however, lies in the possibility they represent, that singularities might not be final endpoints, but gateways to somewhere else entirely. Our universe might have more rooms than we can perceive. String theory, one of the most ambitious frameworks in physics, suggests that the fundamental building blocks of reality are not point-like particles but incredibly tiny, vibrating strings. For the mathematics of this theory to work, it requires more than the 3 spatial dimensions we experience. It proposes a cosmos with 10 or even 26 dimensions, all curled up into a space so small it is hidden from our view. This is not just an abstract idea, it opens a new playground for wormholes. In our familiar 3-dimensional world, a wormhole is visualized as a tunnel or a throat. But in the higher dimensional landscape of string theory, a wormhole could be something far more complex and strange. It might not be a simple tunnel through space, but a structure connecting entire membranes of reality called brains. Think of our universe not as an isolated sheet, but as one page in an infinite cosmic book. A higher dimensional wormhole could be a bridge connecting our page, our brain, to another page entirely, a separate universe with its own laws and particles. This reimagining of the wormhole transforms it from a mere shortcut to a gateway between worlds. String theory also offers a potential escape from the exotic matter problem. The intricate vibrations of strings and the specific way they wrap around these extra dimensions could generate forces and fields that act to stabilize a wormhole's throat from the inside. The geometry of these hidden dimensions themselves might provide the necessary structural support, a kind of cosmic architecture that uses the fabric of higher dimensional space to prevent the tunnel from collapsing. In this view, we would not need to line the wormhole with a mysterious substance. The stability could be a natural consequence of the universe's true, multi-dimensional nature. The challenge, of course, is that these extra dimensions are, for now, purely theoretical. We have no way to directly observe or interact with them. Yet if string theory is correct, then every wormhole might be a shimmering cathedral built not in 3 dimensions, but in 10. Its true form and function visible only from a perspective we have yet to attain. Stephen Hawking was deeply troubled by the paradoxes that time travel invited, so he proposed a cosmic rule to forbid them entirely. He called it the chronology protection conjecture, a principle suggesting the laws of physics have a built-in mechanism to prevent journeys to the past. Hawking essentially argued that the universe has a cosmic censor, a set of fundamental rules that actively destroys any potential time machine before it can be used. The proposed mechanism for this censorship lies in the bizarre quantum nature of empty space. Remember the virtual particles that flicker in and out of existence. Now imagine a wormhole configured as a time machine, creating a closed loop in time. As particles travel on these looping paths, they could potentially interact with their own past versions. Hawking showed that the quantum fluctuations in this scenario would not cancel each other out. Instead, they would feed back into the loop, amplifying each other over and over in a runaway cycle. This would cause the energy density to soar, building towards an infinite value at the heart of the wormhole. This isn't just a power surge, it's a fundamental instability. The vacuum of space itself would rebel, generating a cataclysmic feedback loop of energy that would rip the wormhole apart or collapse it into a singularity long before a single paradox could occur. It's as if time itself has an immune system, one that identifies the infection of a causality loop and triggers a violent fever to burn it out. The conjecture remains unproven, but it presents a compelling argument. Perhaps the reason we never encounter time travelers is not because the technology is impossible, but because the universe is ruthlessly efficient at deleting the very pathways that would allow them to exist. The same force ripping the cosmos apart might also hold the keys to its greatest shortcuts. Dark energy, the mysterious presence causing the universe's expansion to accelerate, represents one of physics' deepest puzzles. Its nature is fundamentally repulsive, a kind of anti-gravity that pushes space itself outward. This eerily echoes the property we desperately need for a stable wormhole, the negative pressure of exotic matter. Could these two cosmic mysteries be different faces of the same phenomenon? Some theories boldly propose that dark energy is not just an analogy, it is the very substance needed to prop open a wormhole's throat. Imagine a natural wormhole, a primordial relic from the Big Bang. As the universe expands, dark energy permeates every cubic inch of vacuum, exerting its subtle push. If this repulsive force were concentrated within the narrow gateway of a wormhole, it could act as a permanent counterweight to gravity's crushing grip. The energy needed to stabilize a tunnel might not require a super-advanced civilization after all. It could be flooding the universe already, a free and abundant resource woven into the fabric of space itself. This idea transforms our vision of these structures. A traversable wormhole would no longer be an isolated engineering marvel, but a natural feature of an accelerating cosmos. Its stability would be intrinsically linked to the same fundamental force that dictates the ultimate fate of everything. The immense scale of the challenge, however, becomes immediately apparent. To harness dark energy in this way, you would likely need to manipulate it on a staggering scale, perhaps even shaping the geometry of the wormhole itself to focus and amplify its effects. We are speaking of controlling the force that governs the expansion of galaxies, yet this speculative link offers a breathtaking possibility. The very mechanism that is driving galaxies away from each other could be the same force that brings two distant points intimately close, creating a cosmic irony of unimaginable proportions. The universe may offer not one, but two distinct kinds of cosmic shortcuts. On one hand, we have the classic tunnels of science fiction, known as Lorentzian wormholes. These are the structures we have been discussing, the ones that emerge as direct, though fragile, solutions to Einstein's field equations. A Lorentzian wormhole is a passage through real space and real time, a tunnel you could theoretically enter at one moment and exit from the next, assuming it could be stabilized. It is the physical bridge connecting two distant points in our four-dimensional reality, the kind of gateway a starship might one day traverse. This is the wormhole of our common imagination, a dynamic structure woven into the fabric of the cosmos we directly experience. Yet there exists another, far more abstract version of this concept, born from the quest to unite gravity with quantum mechanics. These are Euclidean wormholes, and they operate in a domain called imaginary time. Imaginary time is not time as we live it, but a mathematical trick, a rotation of the time axis into a fourth spatial dimension. It is a powerful conceptual tool that simplifies the complex equations of quantum gravity. In this strange, timeless landscape, a Euclidean wormhole is not a tunnel you could travel through. Instead, it represents a momentary, spontaneous connection in the underlying quantum geometry of the universe. Think of it this way: a Lorentzian wormhole is like a completed bridge across a canyon, a structure that exists in the landscape. A Euclidean wormhole, however, is more like the architect's initial sketch, a fleeting connection that appears only in the blueprint of reality itself, a blueprint drawn in a language we are still learning to read. These quantum wormholes are thought to be everywhere, constantly bubbling in and out of existence at scales 1 billion times smaller than an atom. They are the fundamental components of the space-time foam, a seething, chaotic substrate where the very concepts of before and after lose their meaning. While a Lorentzian wormhole promises a journey across the galaxy, a Euclidean wormhole offers a glimpse into the very origin of space and time, suggesting that what we perceive as a smooth, continuous fabric is actually a tapestry of countless transient quantum threads. A black hole's shadow is the darkest place in the universe, but is it truly a final destination? Some physicists propose a radical alternative, that what we perceive as black holes are not endpoints at all, but the entrances to wormholes. This idea emerges from a startling fact. The observational signatures for both objects would be nearly identical from a distance. Each would possess an event horizon, a point of no return for light. Each would warp the starlight around it through gravitational lensing, creating a distinctive halo. To any telescope, a wormhole entrance and a black hole would appear as the same cosmic phantom, a dark silhouette against a distorted backdrop of stars. The critical difference lies in what happens at the very center. A classical black hole is thought to contain a singularity, a point of infinite density where the laws of physics break down. A traversable wormhole, however, would have no singularity. Instead of a crushing-in point, it would feature a tunnel, a throat leading somewhere else. The challenge for astronomers is finding a way to peer past the event horizon to tell them apart. One promising method involves listening for echoes. When two black holes merge, they create gravitational waves, ripples in space-time. These waves are thought to ring down in a specific, clean pattern as they settle into the new, larger black hole. But if the object were a wormhole, the gravitational waves could behave differently. Some of the energy might reflect off the wormhole's throat, the gateway to the tunnel, creating faint echoes in the signal long after the main event. It would be like hearing a whisper rebound from a distant cavern, a telltale sign that there is not a solid wall at the center, but a passage. Researchers are actively sifting through data from observatories like LIGO and Virgo, searching for these subtle reverberations hidden within the cosmic din. Finding one would not just confirm an alternative to black holes, it would revolutionize our understanding of what lies at the heart of these gravitational giants. A blueprint for a wormhole arrives from nowhere, handed to you by your future self. You study it, you build the machine, and you step through the gateway, only to find yourself in the past, ready to hand that same blueprint to your younger self. Where did the design originally come from? This is the self-creation paradox, a loop of existence with no clear beginning. The information, the object, or even the person involved has no point of origin. It simply exists in a closed, timeless circle forever. Our entire understanding of reality is built on a simple foundation, cause and effect. One event leads to another in an unbroken chain stretching back to the dawn of time. The bootstrap paradox shatters this chain. It suggests that certain things might not have a cause at all. They are just permanent features of the cosmic landscape trapped in an infinite loop. Think of a song you hear for the first time, a melody so beautiful it haunts you. You then travel back in time and teach that song to a young composer who grows up to publish it. You then hear the song in your own time, learn it, and travel back to teach it again. The song was never written by anyone, it was always just there, cycling through time. If such paradoxes are possible, it forces us to question the very nature of invention and discovery. Are some ideas not created, but simply found, waiting in the folds of time for someone to complete the loop? This is not merely a philosophical puzzle, it is a direct challenge to the linear flow of time we take for granted, suggesting that the universe might allow for stories that write themselves with no true author and no first page. The bootstrap paradox taunts us with loops in time, but what if a wormhole offered an escape route not just to another time, but to another reality entirely? This leads us to the staggering idea that wormholes could be bridges to the multiverse. Our entire cosmos, with its hundreds of billions of galaxies, might be just one isolated bubble in a vast, frothing sea of other universes. The theory of cosmic inflation suggests that our universe underwent a period of unimaginably rapid expansion just after the Big Bang. Some models propose this inflationary process never truly stopped, but continues in distant regions, constantly giving birth to new universe bubbles with different properties. These bubbles would be forever separate, expanding away from each other in a meta-space we cannot perceive. A wormhole could theoretically puncture this barrier. It would be a cosmic needle, stitching a thread between the fabric of our universe and the fabric of another. Think of our universe as one room in an infinite hotel. The doors in the hallway are locked and the rooms are moving apart. A wormhole would be a secret passage drilled through the wall, connecting your room directly to another one down the hall or on a completely different floor. Stepping through such a gateway would be more profound than mere interstellar travel. You would be entering a cosmos where the very rules of reality might be rewritten. The other universe could have a different number of dimensions, or a stronger force of gravity, or a faster speed of light. In some, atoms might never have formed, with matter arranged into entirely different structures. In others, time might flow backward or in loops. This provides a breathtaking physical mechanism for something that was once pure speculation. The wormhole becomes the ultimate explorer's tool, a tangible passage to a literally alien physics. The journey, however, would be a voyage into the absolute unknown. There would be no guarantee that the constants of nature on the other side would support your existence. You might emerge into a universe where chemistry is impossible, or where space itself is lethal to the structures that make you. Yet the mere possibility that such connections could exist reshapes our place in the cosmos, suggesting that every black hole shadow or unexplained gravitational echo might not be a dead end, but a doorway to another entire world. Cosmic strings offer a completely different blueprint for a stable wormhole. These are not strings in the everyday sense, but hypothetical cracks in the universe, unimaginably thin filaments of pure energy left over from the Big Bang. A single cosmic string would be narrower than a proton, yet a single inch of it could weigh more than a mountain range. Their existence is predicted by many models of the early cosmos, and if they are real, their gravitational influence would be absolutely monstrous. This raw, concentrated power could be the key to propping open a cosmic tunnel. Picture a wormhole as a delicate soap bubble, constantly on the verge of popping from its own surface tension. Now imagine threading a needle of cosmic string through its center. The immense gravitational pull of the string would pull outward on the throat of the wormhole, acting as a permanent counterforce to the inward crush of gravity. It would be like using the gravity of an entire planet to stretch open a portal, creating a natural, self-sustaining structure. The best part of this theory is its simplicity. It requires no exotic matter, no unfathomable technology. If both cosmic strings and primordial wormholes exist, then the universe could have woven its own stable gateways entirely by accident during its violent birth. These would be ancient, natural monuments, holding themselves open with the leftover scars of creation itself. Of course, finding a cosmic string is another monumental challenge. They would be vanishingly rare, and their detection would rely on spotting the unique way they warp the light from distant galaxies. But the possibility remains that the cosmos solved the wormhole problem for us, leaving behind a network of bridges held open by the most fundamental threads of reality. Deep within the foundation of reality, the smooth fabric of space-time dissolves into chaos. At scales a billion trillion times smaller than an atom, the universe ceases to be a continuous sheet and becomes a seething, effervescent foam. This is the quantum foam hypothesis, a vision of the cosmos so extreme it redefines our idea of empty space. At this incomprehensibly tiny scale, governed by the Planck length, the principles of quantum mechanics and gravity collide. The orderly geometry of general relativity breaks down, replaced by a turbulent, probabilistic froth. Here, the energy of the vacuum itself is in constant, violent fluctuation. These quantum jitters are so powerful that they warp the very geometry of space-time, spontaneously creating and destroying minuscule structures. In this frenzied sea, virtual particles are not the only things flickering in and out of existence. The foam is theorized to be a bubbling soup of virtual black holes and wormholes. These are not the grand, stable tunnels for interstellar travel. They are ephemeral quantum fluctuations, wormholes so incredibly small and short-lived that they form and collapse in a fraction of a second, far too brief for even a single photon to pass through. You can think of it as the foam on a turbulent ocean. From a distance, the ocean's surface looks flat and smooth, but up close, you see it is a chaotic mass of bubbles constantly merging and popping. The quantum foam is the true texture of space-time when viewed at its ultimate resolution. This theory suggests that the empty space between stars, the void within atoms, is not truly empty at all. It is this dynamic, frothing substrate of microscopic tunnels and gravitational pits. The very ground beneath your feet, the air you breathe, is built upon this frenetic, bubbling foundation. Every journey you take, every second that passes, unfolds across a hidden landscape of infinite, transient gateways, a universe more intricate and alive than we could ever perceive. The path through a wormhole might not just bend space, but twist time into a knot. This is the concept of a closed time-like curve, one of the most mind-bending ideas in all of physics. A closed time-like curve is exactly what it sounds like, a path through the cosmos that loops back onto its own past. Think of your own life as a line stretching from birth into the future. A closed time-like curve would be a cosmic detour, a loop that carries you from a point in your future back to a moment in your own personal history. You could, in theory, walk a path that allows you to meet your younger self. Certain configurations of wormholes create these loops inherently. If one mouth of a stable wormhole is accelerated to a significant fraction of light speed and then brought back, as we discussed, the time difference between the two ends creates a bridge not just through space but directly into the past. Walking through the moving mouth would send you to the location of the stationary mouth, but at a time before your journey even began. The wormhole itself becomes the physical embodiment of the loop. This possibility forces us to confront the very nature of free will and destiny. If you can travel back to a point in your own past, was that journey always meant to happen? The moment you arrive and interact with your own timeline, it seems you are fulfilling a predestined sequence of events. Your past self sees you arrive, an event that then becomes a memory, a fixed part of their history that inevitably leads them to make the same journey in their future. This is the universe of strict determinism, where every action is locked in place by the unbreakable chain of cause and effect, a chain that has now tied itself into a perfect, inescapable circle. Some physicists argue this is the only way such paradoxes can be resolved, that the universe simply does not allow for logical inconsistencies, and any attempt to change the past would be physically forbidden. You would find yourself unable to alter events, your actions merely completing the loop that always existed. This challenges our deepest intuitions about choice. Are we the authors of our own lives, or are we merely reading from a script that has already been written, a script that includes our own future attempts to rewrite it? The existence of a closed time-like curve suggests a cosmos where history is not a record of what happened, but a single, immutable tapestry with every thread, including those from the future, woven permanently into the whole. A perfectly engineered wormhole would not be a chaotic cosmic accident, but a precisely crafted object. This is the vision laid out by physicists Michael Morris and Kip Thorne, whose work provided the first rigorous blueprint for a traversable wormhole. Their model is the gold standard, a specific geometric design that defines what a stable, human-passable gateway would actually look like. Picture a perfect sphere hanging in space, its surface shimmering like a distorted mirror. This is the throat of the Morris-Thorne wormhole. If you were to fly towards it, you would not see a tunnel entrance in the traditional sense. Instead, as you approach, the view within the sphere would shift, showing you not the space behind it, but a completely different region of the universe. You would be looking directly through the gateway. The geometry is elegantly simple, connecting two separate, flat regions of space, like our own cosmic neighborhood with this spherical bridge. It is not a wild, twisting vortex, but a structured, smooth corridor through the fabric of reality. The true magic and the immense challenge lies in the precise conditions needed to keep this corridor open. The Morris-Thorne model spells out the exact mathematical requirements for stability. The throat of the wormhole must be lined with a very specific type of exotic matter. This is not just any repulsive substance, but one that must satisfy what is known as the flare-out condition. Imagine the throat of the wormhole as the narrowest part of an hourglass. For it to remain open, the surface of this throat must be pushed outward, flared open against the crushing force of gravity. The exotic matter provides this outward pressure, but it must do so in a way that violates what physicists call the average null energy condition. In plain terms, this means the exotic matter must possess a negative energy density so extreme that, from the perspective of a light beam traveling through the tunnel, the overall energy along its path would be less than zero. This sets an incredibly high bar. The exotic matter cannot be a minor ingredient. It must be the fundamental lining of the entire throat, holding the gateway open with a constant, unwavering repulsive force. The Morris-Thorne wormhole is not just a theory, it is a challenge to physics itself, establishing the definitive benchmark against which all other ideas for traversable wormholes are measured. It tells us that if such shortcuts exist, they are not just holes in space, but masterpieces of cosmic engineering, built to impossibly precise specifications. A photon's journey across the cosmos could take a cosmic shortcut. If light itself could traverse a wormhole, the night sky would become a gallery of optical illusions. Imagine observing a distant, brilliant star. Through normal space, you see its light arriving along a straight, if long, path. But if a wormhole sits between you and that star, some of its light might take the tunnel a vastly quicker route. That same star would appear to you in two places at once, its image duplicated in the sky. One image would be the true position of the star, its light tired from the long journey. The other, a ghostly double, would be the light that cheated, leaping through the wormhole to arrive brighter and sharper. This bizarre effect, called gravitational lensing on a cosmic scale, would be the telltale fingerprint of a hidden gateway. The implications grow even stranger when we consider fleeting cosmic events, like a supernova explosion. Normally, we calculate when such an event should be visible based on its immense distance. But if a wormhole provides a shortcut for its light, the brilliant flash could appear in our telescopes years or even centuries before the light traveling the regular route finally trickles in. We would witness the death of a star long before it was supposed to happen, a cosmic spoiler alert written into the fabric of space itself. Astronomers are already equipped to hunt for these anomalies. Deep space surveys that map billions of galaxies are meticulously scanned for such duplicates, for pairs of objects with perfectly identical properties that defy all conventional explanation. Finding just one such pair, one set of twin stars or galaxies that cannot be explained by any known lensing effect, could be the first solid evidence that we are not just looking at the universe, but through it, glimpsing the architecture of its hidden passageways. The most fundamental rule of the quantum world is that information cannot be destroyed. Every particle, every interaction, is a piece of a cosmic code that must be preserved forever. This principle meets its ultimate challenge at the edge of a black hole, creating a paradox that has divided physicists for decades. When an object falls into a black hole, it vanishes behind the event horizon, seemingly lost forever. But Stephen Hawking showed that black holes slowly evaporate, radiating away their mass until they disappear entirely. This presents a catastrophic question. What happened to all the information that described the objects that fell in? Was it truly obliterated, erased from the universe, violating the core tenet of quantum mechanics? This is the black hole information paradox, a battle between general relativity and quantum theory where one of them must be wrong. A stunning resolution suggests that wormholes are the universe's emergency exit for this information. The proposal is that the information is not lost inside the black hole's singularity. Instead, it is transmitted, almost like a cosmic fax, through a wormhole that connects the interior of the black hole to another region of space-time. This other end might not even be in our own universe. It could be a baby universe, a tiny budding cosmos that inflates from the very act of information transfer. In this model, the black hole is not a terminal vault, but a gateway. As the black hole evaporates, the information is not destroyed. It is meticulously encoded into the Hawking radiation that leaks out, or it is safely deposited into a new, separate reality. The wormhole acts as the hidden channel that preserves the cosmic ledger, ensuring that the universe never truly forgets. The information is always somewhere, just not necessarily anywhere we can ever reach. This idea transforms a black hole from a destructive monster into a cosmic translator, one that may be constantly birthing new universes with every piece of information it swallows, all connected by threads too fine for us to see. These same quantum threads could be woven not in space but in sound. A remarkable branch of physics known as analog gravity seeks to recreate the universe's most extreme phenomena right here on Earth inside a lab. It operates on a powerful principle that the mathematical equations describing wildly different systems can be identical. The flow of a superfluid, a liquid with zero friction, can be made to mimic the warped geometry of space-time around a black hole. In such a setup, scientists can create an event horizon for sound. Just as light cannot escape a black hole's gravitational pull, in this fluid flow, sound waves traveling in one direction are swept backward, unable to move upstream against the current. This is an acoustic black hole. The real magic happens when you configure two of these sonic black holes back to back, creating a flow that mimics the throat of a wormhole. This structure is an acoustic wormhole. It is not a tunnel through real space-time, but a perfect sonic analog. Sound waves, or more precisely, the collective vibrations in the superfluid called phonons, behave exactly as light would in a true gravitational wormhole. They can enter one sonic event horizon, traverse the invisible bridge, and emerge from the other side. This gives physicists an unprecedented testing ground. They can probe questions that are otherwise completely untestable. What happens to quantum information when it falls into a wormhole? Does it get scrambled or does it pass through intact? By studying how phonons behave in these acoustic models, researchers can look for clues about the stability of real wormholes and the fate of information within them. It is a cosmic symphony played in a bucket of helium, a laboratory-scale universe where the deepest secrets of gravity are translated into the language of sound, allowing us to listen in on the hidden mechanics of the cosmos. The violent dance of two black holes could rip a temporary gateway in the fabric of space. When these gravitational titans spiral inward and finally collide, the energy they release is so immense it literally shakes the cosmos, sending out ripples known as gravitational waves. Our detectors like LIGO have already heard the cosmic thunder of these mergers, but hidden within that signal might be a whisper of something far stranger. The theory suggests that in the final, chaotic moments before the two black holes become one, their immense gravitational fields could twist space-time into a knot, briefly forming a wormhole that connects them. It would be a fleeting bridge, a cosmic thread stretched between two collapsing stars, existing for only a fraction of a second before the new, larger black hole settles down and the tunnel pinches shut. This is not a stable gateway for travel, but a spontaneous, violent birth of a shortcut that vanishes almost as soon as it appears. The key to proving this lies in the gravitational wave echo. Think of two bells made of space-time itself. When two black holes merge, they ring like a single, clean bell strike. The tone rises to a crescendo and then quickly fades away in a specific pattern called the ring-down. But if a wormhole formed during that collision, the signal would be different. Some of the gravitational wave energy would not just ring from the surface of the new object. It would travel down the brief wormhole throat, reflect off the inner geometry, and bounce back out, creating a faint, repeating echo following the main event. It would be the difference between hearing a single chime in a quiet room and hearing that same chime in a vast cavern where the sound reverberates off distant walls. Our current detectors are listening for these ghostly reverberations. Future observatories with far greater sensitivity will be able to tune into the universe's background hum with unprecedented clarity. They might catch the distinct signature of a wormhole's birth, a tiny, telltale glitch in the gravitational wave signal that reveals not a final merger, but a momentary gateway, a flash of cosmic architecture revealed in the most powerful explosion since the Big Bang itself. A black hole is the universe's ultimate minimalist. According to the famous no-hair theorem, these gravitational giants are stripped of all complexity, defined by just three simple numbers: their mass, their electric charge, and their spin. Like a cosmic fingerprint, these three values are all you need to know to describe a black hole completely. It has no other distinguishing features, no hidden textures, no internal memory. Everything that falls in is lost, its intricate information seemingly erased from existence. But a wormhole presents a radical challenge to this elegant simplicity. A traversable wormhole could be the exact opposite, a cosmic maximalist. It could possess what physicists whimsically call hair, a term for any additional properties beyond those three basic numbers. This hair would be the internal structure of the wormhole itself, the complex geometry of its throat. Think of the difference between a perfectly smooth, featureless marble and a sprawling, intricate labyrinth. The marble is the black hole, defined by its simple, external properties. The labyrinth is the wormhole, its twisting pathways holding the potential to encode information. Instead of destroying the information of what falls into it, a wormhole's throat could theoretically store it. The very shape of the tunnel, the contours of its warped space, could act as a cosmic hard drive, recording a history of what has passed through. This is not just a minor difference, it is a fundamental clash of ideas with profound implications for a theory of quantum gravity. The no-hair theorem is a cornerstone of classical general relativity. The potential for wormholes to have hair suggests that when quantum mechanics is brought into the picture, this simplicity might be an illusion. The void inside might not be empty at all, but teeming with hidden structure, a secret architecture that preserves the universe's deepest ledger. A silent galaxy presents a profound question. If the universe is so vast and ancient, why does it appear so empty of other intelligent life? This is the core of the Fermi paradox, the puzzling contradiction between the high probability of alien civilizations and our complete lack of evidence for them. Wormholes might offer a startling answer. Imagine a civilization so advanced that it has mastered the architecture of space-time itself. For them, building massive starships to crawl between the stars would seem as primitive as using a wooden raft to cross an ocean. Their true technology would be a network of stable wormholes, a cosmic subway system connecting countless worlds. They would not need to colonize star systems in a way we would recognize, building sprawling cities that glow with energy across the electromagnetic spectrum. Instead, they could simply step through a gateway, their entire civilization existing as a decentralized network of interconnected points. They would not need to broadcast powerful radio signals into the void, a temporary phase in a civilization's development that they would have long outgrown. Their primary mode of communication and travel would be through these tunnels in space-time, a medium that is completely invisible to our telescopes. We are scanning the skies for signs of a civilization that builds fires on the beach while they are quietly traveling in tunnels deep beneath our feet. This could explain the great silence. The cosmos is not empty, it is already fully connected. We are simply on the outside of the network, living in the untraveled countryside, unaware that a bustling interstellar society is thriving just beyond our perception, accessed through doors we have not yet learned to see. This violation of the weak energy condition is not just a technical detail, it is a cosmic rule break. General relativity rests on a set of assumptions about how matter and energy should behave, and one of the most fundamental is the weak energy condition. It is a simple but powerful statement. Energy density must always be positive. It means that from the perspective of any observer, anywhere in the universe, the energy they measure should never drop below zero. This principle underpins our entire understanding of gravity as an attractive force. For a traversable wormhole to exist, this condition must be shattered. The exotic matter holding the throat open requires a persistent macroscopic region of negative energy density, a place where the energy is effectively less than nothing. This creates a deep rift in theoretical physics. On one hand, we have the classical, large-scale world of general relativity, which firmly upholds the weak energy condition. On the other, we have the quantum world, which we know from the Casimir effect can produce tiny, fleeting pockets of negative energy. The central debate raging among physicists is whether these quantum exceptions can be scaled up. Can the strange permissions of the microscopic world be harnessed to create a stable, human-sized violation of this classical rule? The challenge is monumental. Quantum field theory suggests that while negative energy densities are possible, they are always constrained by quantum inequalities, laws that limit the magnitude and duration of such violations. It is as if the universe allows you to overdraw your bank account, but only by a few pennies and only for a fraction of a second. To prop open a wormhole, you would need a massive, sustained overdraft, a permanent region of negative energy that defies these quantum limits. This is the Grand Canyon separating a mathematical possibility from a physical reality. The existence of a traversable wormhole hinges on a question we cannot yet answer. Does the universe, at its most fundamental level, permit such a profound and lasting suspension of its own core rules, or is the weak energy condition an unbreakable law that forever keeps the cosmic doors locked? Rotation warps the very fabric of reality, and a wormhole built from this twisted geometry would be unlike any other. This is the Kerr wormhole, a theoretical gateway born from the mathematical solution for a rotating black hole. Unlike the simple, spherical throat of a Morris Thorne wormhole, a Kerr wormhole is a dynamic, whirling vortex. Its rotation fundamentally reshapes the internal structure, potentially replacing the terrifying point singularity of a classic black hole with something far more intriguing, a ring singularity. Picture this not as a dot of infinite density, but as a donut-shaped hole in the fabric of space-time. Theoretically, an object could pass through the center of this ring without being crushed into oblivion, potentially emerging into a different region of the universe or even a different universe entirely. It is a gateway within a gateway, a cosmic loophole offered by spin, but the journey through such a maelstrom would be a disorienting nightmare. The effect of frame dragging would be overwhelming. As space-time itself is twisted into a whirlpool around the rotating wormhole, any traveler would be caught in the current, dragged around the central ring like a leaf in a cosmic drain. Your sense of direction would become meaningless. The view outside your ship would be a kaleidoscope of insane distortions, with starlight stretched into blinding arcs and the universe itself seeming to spiral around you. This rotation might also be the key to stability. The immense centrifugal forces generated by the spin could help counteract the wormhole's tendency to collapse, providing a natural support that reduces the amount of exotic matter required to hold it open. The Kerr wormhole suggests that the most viable cosmic shortcuts might not be calm, static bridges, but violent, spinning hurricanes of warped space and time, where survival depends on navigating the eye of a gravitational storm. Our reality might be a cosmic projection, a hologram of breathtaking complexity. The holographic principle is one of the most radical ideas in theoretical physics, suggesting that all the information describing our three-dimensional universe, every star, every person, every thought, could be encoded on a distant two-dimensional surface. We are the shimmering image, and that surface is the true reality. This concept redefines the nature of a wormhole in a way that ties directly into the quantum threads we explored earlier. Imagine our universe as the surface of a vast spherical bubble. This is the boundary where information is stored. Now, picture a higher dimensional space, often called the bulk, that contains this bubble. A wormhole in this view is not a tunnel through our three-dimensional space. It is a physical bridge that arcs through the higher dimensional bulk, connecting two distant points on our holographic boundary. The truly astonishing connection lies with quantum entanglement. Recall the ER equals EPR conjecture, where entangled particles are linked by microscopic wormholes. The holographic principle provides the ultimate canvas for this idea. Two entangled particles on our boundary, say on opposite sides of the universe, are not communicating faster than light. Their mysterious connection is a geometric reality in the bulk. A wormhole, a literal bridge in the higher dimensional space, physically joins them. Their instantaneous correlation is simply the universe taking a shortcut through a dimension we cannot perceive. Think of it like this. You are watching a movie projected onto a giant screen. Two characters on opposite sides of the screen seem to have a magical, instant connection. What you cannot see are the wires and circuits behind the screen that physically link them, creating the illusion of magic from your limited perspective. The holographic principle suggests we are those characters, and the wormholes are the hidden wiring of reality. This provides a breathtakingly elegant interpretation for the spookiness of quantum mechanics, transforming an abstract puzzle into a question of cosmic architecture, where every quantum link is a tiny thread woven through the higher dimensional fabric of everything. The universe's most powerful computer might not be built from silicon, but from the very fabric of space-time. Imagine a civilization so advanced that it has moved beyond constructing machines and instead engineers reality itself to perform calculations. This speculative theory proposes that a stabilized wormhole could be transformed into the ultimate quantum computer. The principles behind this are as profound as they are complex. A standard quantum computer uses quantum bits or qubits which can exist in a state of 0, 1, or both simultaneously thanks to superposition. Now amplify that concept to a cosmic scale. The interior geometry of a wormhole's throat is not a smooth, simple tunnel. According to some models, it could be a labyrinth of unimaginable complexity, a dynamic structure where every possible path and configuration represents a different quantum state. The number of these potential states, defined by the warps and curves in space-time, would be astronomically vast, far exceeding the number of particles in our observable universe. Harnessing this internal landscape would be like having access to an infinite number of qubits, all interconnected through the wormhole's unique geometry. Such a system would not just be a faster computer, it would be a fundamentally different kind of processor. It could solve problems in an instant that would take a conventional quantum computer the lifetime of the universe to crack. It might model the evolution of galaxies with perfect accuracy, or map the exact conditions of the Big Bang. The most staggering possibility is that it could run a simulation so detailed and complex that it would be indistinguishable from a real universe, potentially birthing entire cosmos within its warped computational space. This transforms the wormhole from a mere transportation device into a cosmic engine of creation, a tool that doesn't just traverse reality, but actively designs and defines it. The journey through a wormhole's throat would be a sensory assault unlike any other. Your first sensation would be an immense stretching pull, a tidal force trying to draw you out like taffy. This is the relentless grip of gravity, testing the structural integrity of your ship and your own body. To survive, your vessel would need to generate an artificial gravity field of immense power, a stable bubble within the chaos, just to keep you from being spaghettified into a stream of atoms. Outside your viewport, the tunnel itself would not be a dark passage. the walls would likely glow with the light of every star whose radiation has ever fallen into the gateway, trapped and amplified as it echoes through the warped geometry. It would be a kaleidoscope of twisted starlight, a river of pure energy flowing around your protective bubble. The most profound moment would be the view ahead. The star system that is your destination would not appear as a distant point of light. Instead, it would be a window that rapidly expands to fill your entire field of vision. You would watch as a single star blossoms into a full solar system, its planets swinging into view in a matter of seconds, an entire cosmos unfolding before you as you approach the exit. But this breathtaking vista comes with a deadly navigational challenge. The center of the wormhole's throat is a precarious balance. Veer too close to the walls and the tidal forces could still shred your ship. But the true danger lies in drifting towards the very center of the tunnel. In many theoretical models, a central pinch exists, a region where the fabric of space-time is at its most strained. Stray into this zone and you could be funneled not toward your destination, but toward a singularity, a point of infinite density that would be your end. Piloting through a wormhole would be less like flying a plane and more like navigating a raft through a raging whirlpool, where the safe channel is a narrow, invisible path that demands perfect precision. One miscalculation and the cosmic shortcut becomes a perfect, inescapable trap. A hidden cosmic law may forbid the universe from exposing its deepest secrets. This is the principle of cosmic censorship, a bold conjecture that proposes nature abhors a naked singularity. The idea is simple yet profound, that every point of infinite density, where the laws of physics break down, must be permanently hidden from our view, veiled behind the one-way curtain of an event horizon. A black hole is the perfect citizen, its terrifying singularity safely locked away where no outside observer can ever see it. A traversable wormhole, however, would be the ultimate cosmic rebel. Its very existence would flout this rule. For a wormhole to be passable, it cannot have a destructive singularity blocking the path. The throat must be clear, a smooth tunnel through space-time. This exposes the universe's raw gravitational machinery. Instead of a hidden singularity, you have a gateway that lays bare the warped geometry of space for anyone to enter and witness. It is a naked gateway, a structure that cosmic censorship was designed to forbid. The debate this sparks cuts to the heart of theoretical physics. Is cosmic censorship a fundamental law of nature, an unbreakable rule that protects causality and predictability? Or is it merely a suggestion, a guideline that the universe sometimes ignores, allowing for the existence of these incredible structures? If traversable wormholes are possible, then the cosmos is far more open and accessible than we thought, a place where the deepest workings of gravity are not hidden away but available for exploration. If cosmic censorship holds true, then every potential wormhole must inevitably collapse, crush, or otherwise disguise itself as a black hole, forever keeping the universe's most dramatic shortcuts locked and hidden from view. The smallest conceivable wormhole would be a ghost in the quantum machinery of the universe. It would exist at the Planck length, a scale so tiny it is the absolute limit where our current laws of physics break down. To visualize this scale, picture shrinking down to the size of an atom, then shrinking again a billion times. At this incomprehensible resolution, space-time is not smooth. It becomes a seething, turbulent froth, the quantum foam we mentioned earlier, and flickering within this foam would be countless Planck wormholes. These are not tunnels for travel. They are ephemeral quantum fluctuations, forming and vanishing in a span of time so brief it has no meaning in our human experience. A single photon, the particle of light itself, is vastly too large to ever pass through one. These wormholes are the fundamental stitches in the fabric of reality, appearing and disappearing like bubbles in a boiling pot. Their existence is governed entirely by a theory we do not yet possess, a complete theory of quantum gravity. This is the holy grail of modern physics, the framework that would finally marry the cosmic rules of Einstein's general relativity with the probabilistic weirdness of quantum mechanics. Understanding these Planck scale structures is not just an academic exercise, it is considered the master key. If we could mathematically describe how space-time behaves at this ultimate resolution, including how these tiny wormholes form and interact, we would have unlocked the unified theory. We would see how the grand curvature of gravity emerges from the frenetic dance of these quantum entities. It is a profound idea that the gravity holding galaxies together might be the collective effect of an infinite number of vanishingly small gateways, popping in and out of existence everywhere at once. This means the empty space around you is not truly empty, but a dynamic, living geometry, its true nature written in a language of wormholes we are only beginning to decipher. Every cup of coffee cooling in a quiet room reminds us that time has a preferred direction. This is the arrow of time, an indelible feature of our universe rooted in the second law of thermodynamics, which states that entropy or disorder always increases. The cream mixes into the coffee, it never unmixes. The universe moves from a state of order to a state of disorder, and this irreversible flow gives our lives a sense of past and future. Now consider stepping into a wormhole that sends you to the past. From your personal perspective, you are simply taking a journey, but from the universe's perspective, you are performing a bizarre trick. You are moving from a future of higher entropy back to a past of lower entropy. It appears as though you are causing a local reversal of the universal trend, like watching a shattered glass spontaneously reassemble. This is the core of the paradox. How can a wormhole allow travel that seems to violate the most fundamental law of cosmic progress? Physicists like Stephen Hawking have argued that the universe possesses a kind of cosmic immune system to prevent such violations. The proposed mechanism ties back to the very stability of the wormhole itself. The immense energy fluctuations required to create a path to the past would be so catastrophic that they would trigger a feedback loop of radiation, instantly destroying the wormhole before any entropy-reversing journey could be completed. The universe would rather obliterate the gateway than allow a single paradox to unfold. Another compelling idea suggests that the psychological arrow of time, our own perception of past and future, is inextricably linked to the thermodynamic arrow. If you were to travel to the past through a wormhole, your own consciousness and memory would still operate within the increasing entropy of your personal timeline. You would remember the future you came from, a state of higher disorder, and perceive the past as ordered, but you could never actually cause the universe to globally reverse its entropic flow. Your journey would be a bubble of consistent experience within the grand, irreversible current of cosmic time. The wormhole, then, might not be a machine for reversing time's arrow, but a structure that allows for a detour along its one-way street, a detour that the universe carefully polices to ensure the street never truly runs backward. Dark matter's invisible grip holds entire galaxies together, yet we have never seen it directly. This mysterious substance, making up over a quarter of the cosmos, might be hiding a secret architecture. Some theoretical models suggest dark matter is not a uniform cloud, but could form intricate structures through its own gravitational pull. Within the vast halos surrounding galaxies, regions of extremely dense dark matter could theoretically collapse. This collapse would not form a black hole, since dark matter does not interact with light or normal matter in that way. Instead, the immense concentration of mass could warp space-time so severely that it pinches off, forming a tunnel. This would be a wormhole born from the universe's most abundant yet elusive material, woven from the fabric of the dark cosmos itself. The stability of such a gateway could come from the unique properties of dark matter itself. Certain hypothetical particles, like actions or sterile neutrinos, could theoretically generate a subtle negative pressure through their quantum behavior. This is not the exotic matter we would need to manufacture, but a natural, inherent trait of the dark matter field. Its pervasive gravitational influence would provide the curvature for the tunnel, while its intrinsic quantum pressure acts as the support beam, holding the throat open against collapse. This means the very stuff that binds galaxies could be secretly stitching the universe together with a network of stable passageways. These wormholes would not be found in empty intergalactic space. They would be nested deep within the luminous hearts of galactic dark matter halos, hidden in plain sight amongst the countless stars. We might be orbiting one right now, our solar system swinging past a cosmic gateway every 250 million years as we circle the Milky Way, completely unaware of the shortcut lurking in the darkness between the stars. A perfectly aimed shot could shatter the logic of time itself. This is the Polchinski paradox, a brilliant thought experiment that strips time travel down to its most elemental conflict. Physicist Joseph Polchinski imagined a simple scenario involving a billiard ball and a wormhole configured as a time machine. Picture the wormhole's two mouths, mouth A and mouth B, placed in the same room. Mouth B leads 5 minutes into the past of mouth A. Now you roll a single billiard ball on a perfect trajectory. It glides across the table, vanishes into mouth B, and emerges from mouth A 5 minutes in the past. But here is the devastating twist. The ball emerges on a collision course with its own younger self, still rolling toward the wormhole. The impact is direct and forceful. The younger ball is knocked cleanly off its path, never reaching mouth B. This creates an insurmountable logical contradiction. If the younger ball never enters the wormhole, then the older ball that emerged to block it could never have existed. The entire sequence unravels from both ends, leaving no clear origin for the event. It is a perfect, self-canceling loop that seems to forbid its own existence. The paradox suggests that any form of time travel that allows you to change the past is fundamentally impossible, as it leads directly to these causal nightmares. Yet, quantum mechanics might offer a bizarre escape clause. Some models propose that the universe would not allow the paradox to happen. Instead of a direct blocking collision, the emerging ball might only deliver a glancing blow. It would nudge the younger version just enough to alter its spin or slightly adjust its angle, but not enough to prevent it from entering the wormhole. The younger ball, now slightly scuffed and spinning differently, would still enter mouth B, travel back, and emerge to deliver that exact same glancing blow. The loop is preserved, every event has a cause, and every action is consistent, even if the details are slightly different. The universe finds a stable, self-consistent solution, one where the ball's history is a closed, unbroken circle of cause and effect. The Polchinski paradox reveals that time might not be a fragile thing that breaks under paradox, but a resilient force that simply finds a new, consistent path, no matter how strange the detour. A wormhole might not be a fixed gateway at all, but a wave, a ripple in the cosmos traveling at incredible speed. This theory introduces the idea of gravitational solitons, which are not made of matter, but are self-reinforcing, stable waves in the very fabric of space-time itself. Think of a tsunami wave in the ocean that maintains its shape and power as it travels across entire oceans, refusing to dissipate. A gravitational soliton is like that, a solitary, coherent pulse of warped geometry that moves through the universe, holding its form against the forces that would normally cause it to spread out and fade away. The astonishing proposal is that the complex geometry of a wormhole could be embedded within one of these traveling waves. This means the tunnel itself, the shortcut through space, would not be anchored to any particular star system. It would be a roving gateway hurtling through the galaxy. One moment it could be near a distant nebula, and the next it might be passing through the outer reaches of our own solar system, completely unnoticed. This motion presents the ultimate detection challenge. Our entire search strategy for cosmic anomalies relies on finding something that stays put long enough for us to point our telescopes at it. A moving wormhole would be a ghost, here one instant and gone the next. How could we ever track a shimmering distortion that is itself racing away at a significant fraction of light speed? Its signature would be a fleeting gravitational lensing effect, a momentary duplication of a star that vanishes before we can even confirm it. This transforms our image of the cosmos from a static map to a dynamic, flowing landscape where the very pathways between stars are in constant motion, fleeting opportunities in an ever-shifting celestial sea. A single electron could be every electron. This is the breathtakingly simple premise of the one-electron universe hypothesis, a classic speculation that reimagines the entire cosmos. Picture every electron and its antimatter partner, the positron, not as countless distinct particles, but as the fleeting appearances of just one single entity. This one electron would be weaving a fantastically complex path through all of time and space, moving forward in time as the familiar electron, and then reversing its temporal direction to appear as a positron. The entire cosmic population of these particles would be the shimmering trail of this one solitary traveler. But how could it possibly accomplish such a journey? Wormholes provide the physical architecture for this incredible idea. The path of this single electron would not be a simple, meandering line. It would be a web, a labyrinth of microscopic wormholes stitching through the fabric of space-time. Each time the electron needs to reverse its direction in time, it would dive into one of these tiny gateways, emerging at a different point in space and a different moment in time, its charge effectively reversed as it pops back into our temporal flow. Every interaction we observe, every electron in every atom of your body and in every distant star, would be a different point where this one fundamental entity pierces through the veil of our perceived reality. This would be the ultimate unification of matter, a cosmic tapestry woven from a single thread, with wormholes as the needle endlessly pulling it through the fabric of everything. The universe would be an unimaginably intricate knot tied with one string. Our reality might be a flat page in a cosmic book we cannot see. String theory suggests we are confined to a three-dimensional membrane or brain, floating within a higher dimensional expanse called the bulk. From our limited perspective, a wormhole is a mysterious tunnel warping through the universe we know. But for a hypothetical being living in the bulk, viewing our brain from the outside, that same wormhole would appear utterly different. It would not look like a tunnel at all. Instead, it would resemble a simple, short arch or a bridge, directly connecting two distant points on our flat cosmic page. What seems to us a long and perilous journey through a hidden corridor is, from this higher vantage point, just a quick hop across a gentle hump in the geometry of reality. This profound shift in perspective solves a deep mystery of how a wormhole functions. We struggle to visualize how 2 points can be brought together without folding the space between them, but from the bulk's perspective, that is exactly what happens. The higher dimensional geometry allows for a shortcut that bypasses our conventional space entirely. It is as if you were a drawing on a piece of paper and someone gently pinched the paper to bring your hand and your foot closer together. You, as the drawing, would still experience the line between them as long and straight, but an outside observer would see the direct connection made by the fold. A wormhole is that pinch made real by the architecture of higher dimensions. This means the true form of a wormhole is not a tunnel within our universe, but a structure that briefly dips out of it, traversing the bulk to reach another location on our brain. The energy required to create such a bridge might be far less from this outside perspective, a simple matter of cosmic engineering that our three-dimensional physics interprets as an impossible feat requiring exotic matter. The universe's greatest shortcuts may not be hidden within our space, but just beyond it in the vast, unseen dimensions that hold our world aloft. The universe might simply refuse to let you break its own rules. This is the core of the Novikov self-consistency principle, proposed by the Russian physicist Igor Novikov. It offers a stark and elegant solution to every time travel paradox we have encountered. The principle states that if time travel to the past is possible, then the universe is fundamentally constrained to prevent any logical contradictions from ever occurring. Your actions in the past were always a part of history. You cannot change what has already happened because you were always there, a hidden participant in the events you remember. Apply this to our wormhole time machine. You decide to travel back to prevent a famous historical event. You step through the gateway armed with knowledge and intent. Yet, according to Novikov, you will fail. Not because of some external force that stops you, but because the universe is a single, self-consistent story. Your attempt to change the event is what inevitably causes it to happen in the exact way it always did. Perhaps you trip at a critical moment, or you are mistaken for someone else, or your actions inadvertently set the very chain of events in motion. The outcome is fixed. Your journey back was not an intervention. It was always a line in the script written from the very beginning. This principle imposes a rigid, deterministic framework on reality. It suggests that the entire timeline is a single, unchangeable block. The feeling of free will we experience is genuine in the moment, but when it comes to time travel, that freedom is an illusion. You are not writing history as you go. You are merely reading your lines from a book that was already complete. Every choice you make about the past was predetermined the moment the wormhole formed. This transforms the time traveler from an active agent into a passive instrument of fate, their journey a closed loop of cause and effect with no loose ends. It is a universe where paradoxes are not just avoided, they are fundamentally impossible because the fabric of reality is woven too tightly to ever unravel. Teleportation is not just science fiction, but a real process happening in quantum labs today. Scientists can take the complete quantum state of one particle and instantly transfer it to another distant particle, effectively teleporting its information. This relies on the spooky connection of entanglement, a phenomenon we now suspect might be underpinned by microscopic wormholes. Now, scale this idea up to a human traveler and a traversable wormhole. The journey through the tunnel would be the ultimate teleportation device. Your entire body, a collection of trillions of atoms arranged in a specific quantum state, would enter the gateway. The wormhole would not simply move your physical form like a train through a tunnel. The extreme warping of space-time inside would dismantle your atomic structure, translating your unique quantum information into a pattern woven into the fabric of the tunnel itself. This information would then race through the shortcut and be perfectly reassembled at the exit, particle by particle, with every memory and thought intact. This raises a profound and unsettling philosophical question. Is the person who steps out the original you, or are they a flawless copy, a perfect reconstruction based on the data that passed through the wormhole? If the original you was deconstructed at the entrance, was that a form of death with a new consciousness awakening at the destination, convinced it is the same person? Or does the continuous thread of your quantum information, preserved through the journey, guarantee that the stream of your consciousness remains unbroken, making you the sole and original traveler? There is no experiment that can distinguish the copy from the original, because every atom and every memory would be identical. The wormhole does not just challenge our understanding of space, it forces us to confront the very nature of self and identity, leaving us to wonder if every journey through the stars would be a leap of faith into a new version of our own existence. A gateway to the past presents a boundary where physics itself loses its voice. This is the Cauchy horizon, a point of no return for predictability. Within a wormhole configured as a time machine, this horizon forms the threshold of the time loop, the moment where the future can begin to influence the past. Once you cross this invisible line, the universe can no longer determine what will happen next based on the initial conditions that came before. The clear, deterministic laws of physics, which have guided the cosmos since the Big Bang, simply break down. It is the edge of the map, and beyond it, the rules we rely on become undefined. Imagine you are watching a film where the final scene has already been written, but as the movie plays, the ending starts rewriting the beginning in real time. The narrative logic collapses into an unpredictable feedback loop. Inside the Cauchy horizon, cause and effect no longer flow in one direction. A particle could emerge from the future and collide with its own past version, creating a chain of events with no clear origin. The very fabric of reality becomes logically unstable, a chaotic region where anything might be possible because the physics has no single, consistent solution. This inherent chaos may contain its own destruction. As energy, whether starlight or random quantum fluctuations, circulates through the wormhole's time loop, it repeatedly crosses the Cauchy horizon. With each pass, the energy gets compressed, its waves squeezed tighter and tighter. This process, known as blue shifting, amplifies the energy dramatically, transforming a faint whisper of light into an intense, concentrated scream of radiation. The energy density would skyrocket towards infinity, creating a wall of fire at the horizon. This isn't just a barrier, it's a catastrophic instability. The infinite buildup would likely trigger a violent reaction, either ripping the wormhole apart or crushing it into a singularity. This provides a powerful physical mechanism for Stephen Hawking's chronology protection conjecture. The universe may not need a complex law to forbid time travel. It simply engineers its potential pathways to self-destruct the moment they become paradoxical. The Cauchy horizon acts as a cosmic fuse, burning out at the first sign of a logical inconsistency, ensuring that the timeline we experience remains a single, consistent story. Our universe's delicate balance might be the very reason its doors remain locked. This is the anthropic principle applied to wormholes, a cosmic explanation for the great silence and stillness we observe. The principle suggests that the fundamental constants of our universe, the strength of gravity, the mass of an electron, the speed of light, appear finely tuned for one specific outcome, the emergence of conscious life. We exist to observe a universe that allows for our existence. Now, extend this logic to cosmic shortcuts. What if stable, traversable wormholes are not just difficult to build, but are fundamentally incompatible with a life-bearing cosmos? Consider the chaos if such gateways were common. The universe would be crisscrossed with pathways, with time travelers from the future constantly appearing in the past. The timeline would be a tangled mess of interference and paradox, the consistent, predictable environment that allowed the first single-celled organisms to form in a quiet pond, that allowed dinosaurs to roam for millions of years, that allowed our own ancestors to slowly evolve, would be impossible. The constant traffic of objects and information from any possible future would render the past unstable, a place where cause and effect are meaningless. In such a reality, the long, unbroken chain of events required for a planet to cool, for water to pool, and for complex chemistry to begin would be shattered. Our universe feels so vast and ancient because it is, with galaxies separated by voids that take light eons to cross. This immense, slow-moving scale provides the stable nursery life needed. If wormholes were readily available, that vastness would be an illusion, and the nursery would be in a state of perpetual, unpredictable storm. So we find ourselves in a quiet cosmos not because wormholes are impossible, but perhaps because in any universe where they are easy, no one is ever around to wonder about them. The very fact that we are here to ask the question may be the strongest evidence that the universe protects its own history by keeping its shortcuts sealed. Some of the universe's most powerful bullets might be fired from hidden cosmic guns. For over a century, scientists have detected ultra-high-energy cosmic rays, individual subatomic particles carrying as much energy as a professionally thrown baseball, all packed into a single, invisible speck. These particles arrive from deep space with incomprehensible force, and their origins have remained one of astronomy's most enduring puzzles. No known astrophysical object, not a supernova, not a pulsar, seems capable of accelerating a particle to such an extreme. But a wormhole's throat could be the universe's ultimate particle accelerator. Picture the immense gravitational chaos within that tunnel, a maelstrom of warped space and twisted magnetic fields. A lone proton, perhaps a piece of interstellar dust that strayed too close, gets caught in this gravitational tide. It isn't simply carried through, it is whipped and slingshotted, gaining speed with every bounce off the violently contorted walls of the tunnel. The same tidal forces that threaten to tear a starship apart would act on this tiny particle like an endless series of gravitational catapults. By the time it exits the wormhole's other mouth, it is no longer a drifting speck. It is a relativistic bullet shot across the cosmos at a velocity infinitesimally close to the speed of light. This would explain why we cannot trace these cosmic rays back to a visible source. We are not seeing the gun, we are seeing the bullet that fired out of its hidden barrel. The particle's trajectory points back to an empty patch of sky because the true origin is not a star or a galaxy, but a gateway, a cosmic lens that focused a random bit of matter into a weapon of immense power. The empty void of space might be filled with the silent, high-velocity hail from countless invisible doorways. A wormhole is not a permanent monument, but a living thing with its own cosmic birth, life, and death. Its story begins in the most chaotic nursery imaginable, the quantum foam. Here, in the seething vacuum at the Planck scale, a microscopic wormhole flickers into existence. It is a random fluctuation, a tiny knot in space-time that forms from nothing and vanishes just as quickly. But if conditions are just right, perhaps in the intense heat of the early universe, one of these quantum knots could be stretched and inflated by the rapid expansion of the cosmos. It is pulled from the quantum foam and blown up to a macroscopic size, becoming a true gateway, a primordial wormhole threading through the newborn universe. For this infant wormhole to survive its violent birth and enter a stable phase, it needs support. Perhaps it captures a thread of cosmic string during its formation, whose immense gravity holds the throat open. Or maybe the repulsive force of dark energy permeating the vacuum provides just enough negative pressure to counteract the gravitational squeeze. This is the wormhole's mature life, a period of potential stability that could last for billions of years. During this long adulthood, it hangs in space as a silent, shimmering gateway, a possible shortcut for any civilization advanced enough to find it and brave enough to enter. But nothing in the universe lasts forever. The stability is a delicate balance, and eventually it must fail. The exotic matter lining its throat might slowly decay. The cosmic string threading its center could snap under unimaginable tension. The balance tips and the relentless force of gravity finally wins. The wormhole's throat begins to narrow, the walls of the tunnel rushing inward. For any traveler inside, it would be a terrifying conclusion, a race against a collapsing corridor of space-time. The end comes when the throat pinches off completely, severing the connection between its two mouths. The death of a wormhole is not a quiet fading. As the throat contracts to a microscopic point, the energies involved become astronomical. This final, violent pinch could trigger a flash of Hawking radiation, a burst of energy and particles signaling its demise. But another, even more spectacular, fate is possible. The pinching off might not simply sever a connection within our universe. Instead, the searing energy of the collapse could be so intense that it inflates a new region of space-time, a baby universe that buds off from our own. The dying wormhole becomes a cosmic seed, giving birth to an entirely new cosmos with its own laws and history, forever separated from the universe that created it. The end of one gateway could be the Big Bang for another. Our universe is built from an overwhelming surplus of matter, a fact so fundamental we rarely question its strangeness. Every particle of dust, every star, and every one of us is made of matter, yet we find almost no antimatter in the cosmos. This is the puzzle of baryon asymmetry, one of the greatest unsolved mysteries in physics. The laws of nature, as we understand them, treat matter and antimatter almost identically, so the Big Bang should have created them in equal amounts, leaving them to annihilate each other in a flash of pure energy. We should not exist. Something must have tipped the scales. One of the most speculative theories points to the chaotic architecture of the infant cosmos, suggesting that wormholes may have acted as cosmic sorting machines. In the first searing moments after the Big Bang, the universe was a dense, turbulent soup of particles and energy, a place where space-time itself was a frothing sea of quantum foam. Within this frenzy, countless microscopic wormholes would have been constantly forming and collapsing. The theory proposes that these fleeting gateways did not just connect points in space, they may have distinguished between matter and antimatter. Picture a wormhole not as a neutral tunnel, but as a filter with a specific charge. As particles surge through the primordial plasma, a matter particle, like a proton, might have been funneled into one of these wormholes, while its antimatter counterpart, an antiproton, was repelled or shunted into a different gateway. This separation could have happened on a colossal scale, with entire streams of matter and antimatter being routed down different cosmic drains. The matter that makes up our world might be what remained after the rest was siphoned away. Where did it all go? The antimatter could have been channeled into entirely separate regions of our own universe, vast, invisible domains of antistars and antiplanets forever beyond our observational reach. Or, in an even more radical possibility, the wormholes could have funneled the antimatter into different baby universes entirely, each one born with its own dominant substance. Our universe, in this view, is not the whole story, but merely the matter-rich branch of a much larger, more balanced multiverse. We are not the standard, but the anomaly, a single pocket of surplus left behind by a cosmic sorting process that occurred when reality was still taking its first breath. A unified theory of physics must pass through the throat of a wormhole. This is the ultimate crucible for any idea that seeks to marry the cosmic force of gravity with the probabilistic rules of the quantum world. When we follow the equations of general relativity into the heart of one of these gateways, they predict a catastrophic failure, a point of infinite density where our understanding simply stops. Yet we know that for a wormhole to be traversable, this cannot be the final answer. Something must intervene to smooth out that violent pinch and keep the corridor open. That something is the domain of quantum gravity. The searing, microscopic environment of the wormhole's narrowest point is where the fabric of space-time is stretched to its absolute limit. Here, the smooth geometry described by Einstein dissolves into the chaotic frenzy of the quantum foam. A theory that cannot mathematically describe what happens in this region, how gravity behaves when space-time is knotted into a tunnel, is a theory that remains incomplete. It is like having a detailed map of a continent that shows a vast blank space labeled "Here be dragons." The wormhole throat is that dragon, and a true theory of everything must be brave enough to chart it. This transforms the wormhole from a mere speculative wonder into the most important diagnostic tool in fundamental physics. If you claim to have a theory of quantum gravity, you must be able to show me your math for the wormhole. Can it calculate the precise energy conditions needed to hold the throat open? Does it predict how information would behave as it passes through that quantum storm? The wormhole presents a set of questions so sharp and specific that any flawed theory will inevitably snag on them. Therefore, the journey to understand these cosmic shortcuts is not a side quest. It is the central mission. Unlocking the secret of the wormhole is not just about building a stargate. It is about reading the final, missing page of the universe's own operating manual. The very act of looking at a quantum system seems to change its behavior, a mystery that lies at the heart of consciousness itself. Now, push that idea to its absolute limit within the warped geometry of a wormhole. Could a conscious mind, simply by being present and observing, influence the stability of the tunnel around it? This speculation ventures into a realm where physics and philosophy blur. The quantum measurement problem suggests that a particle exists in a haze of probabilities until a conscious observer measures it, forcing it to choose a definite state. Apply this to the exotic matter lining a wormhole's throat, a substance that is itself a quantum phenomenon. The presence of a conscious traveler could, in theory, act as a continuous measurement, collapsing the fragile quantum wave functions that give the exotic matter its reality. Your awareness might be the very thing that solidifies the tunnel, turning a flickering possibility into a stable passage, or it could have the opposite effect. Your observation might disrupt the delicate balance, causing the negative energy density to fluctuate wildly and triggering a catastrophic collapse. In this view, traversing a wormhole would be less like flying a ship and more like a high-stakes meditation, where the focused state of your own mind becomes a critical component of the journey's success. An even more radical idea suggests that the wormhole itself could possess a form of rudimentary consciousness. Its throat is not an empty corridor, but an incredibly complex informational structure, a labyrinth of quantum states woven into the fabric of space-time. If consciousness arises from the integrated processing of information in our brains, could a structure as complex as a stable wormhole develop its own kind of proto-awareness? It would not think in words or images, but in the language of geometry and gravity, its thoughts the shifting contours of its own tunnel. This gateway would not be a mere tool, but a living entity, a conscious corridor that a traveler must somehow communicate with or appease to secure safe passage. Such concepts stretch our understanding of reality to the breaking point, forcing us to consider whether the cosmos is not just a physical place, but a mental one as well, where the deepest journeys require not just advanced technology, but an enlightened mind. A single stable wormhole would rewrite our future, but a network of them would redefine civilization itself. The first successful creation of a traversable gateway would immediately present an irresistible next step, the construction of an interstellar transit system. The engineering challenges would be beyond monumental, yet the vision is clear. Each new wormhole would need to be meticulously positioned, its two mouths carefully transported to their destinations. One mouth might remain in a stable orbit around Earth, a grand central station for all of humanity, while the other is towed by a slow, powerful vessel on a years-long journey to a new world, perhaps a terraformed Mars or the icy oceans of Europa. Once in place, the gateway is activated, and a journey that once took months or millennia becomes a single step. The sociological upheaval would be instantaneous and profound. The very concept of distance would become obsolete. You could have breakfast in your home in New York, take a short walk through a gateway, and have lunch with a friend living in a domed city on a planet orbiting Alpha Centauri. Families would be spread across light years, yet remain as close as neighbors. The term interstellar species would no longer be an aspiration, it would be a simple statement of fact. This network would force a complete reimagining of economics, law, and culture. A unified human government might finally become a necessity to manage the traffic of people, goods, and ideas between worlds. Or conversely, the vast distances that once separated us could be replaced by an even more complex web of alliances and conflicts, with each connected world developing its own unique identity while remaining a short walk from everyone else. The Earth would no longer be our solitary cradle, but the bustling, ancient heart of a connected galaxy, its culture radiating out through the gateways to shape a truly universal human experience. The laws of physics feel absolute, but what if they are simply the source code of a grand simulation running on a computer of unimaginable power? This is the simulation hypothesis, a mind-bending proposal that our entire universe is a digital construct. Within this framework, a wormhole takes on a startling new identity. It might not be a natural cosmic structure at all, but a feature deliberately engineered into the system, a debugging tool for the universe's creators. Imagine the programmers of this reality needing to examine a distant sector of their simulation. Instead of waiting for light to travel across billions of lines of code, they could instantiate a wormhole, a direct data transfer conduit linking 2 points. The exotic matter holding it open could simply be a line of code that locally inverts the simulation's fundamental gravitational constant, a temporary patch that allows the shortcut to exist. All the properties that make wormholes seem so paradoxical to us, their defiance of causality and their need for impossible energies, become perfectly logical. They are not breaking the laws of physics, they are utilizing administrative privileges to temporarily rewrite them. A wormhole could be a backdoor left open in the cosmic code, a glitch that has been intentionally permitted for maintenance or observation. Our struggle to reconcile wormholes with our understanding of reality might be the ultimate clue. We are like characters in a video game trying to understand the developer console that spawned us. Our physics nothing more than the user-friendly interface hiding the raw, editable code beneath. The existence of a stable wormhole would not just prove Einstein right, it might prove we are living in someone else's creation. The ultimate fate of anything that enters a wormhole remains the final, terrifying unknown. You step into the shimmering gateway with a destination in mind, but the universe may have other plans. One possibility is the simple success story, a clean transit that deposits you, intact and sane, into another time or a distant star system. Yet this tidy outcome is perhaps the least likely in a cosmos built on quantum uncertainty and violent forces. A far more probable end is disintegration. The same tidal forces that stretch the fabric of space could stretch your molecular structure, pulling every atom in your body along a different gravitational gradient. You would unravel into a stream of fundamental particles, your physical form dissolving into a cloud of quarks and electrons, your consciousness extinguished as your information is scrambled into cosmic noise. This matter would then be sprayed out the other side, not as a person, but as a burst of exotic radiation, a silent testament to a journey that failed. There is another, stranger destiny. You might not be destroyed, but incorporated. The wormhole's exotic structure could absorb you, weaving your atomic pattern into the very fabric of the tunnel's lining. Your essence would become a permanent part of the gateway, a ghost in the machine, your memories and thoughts frozen forever within the warped geometry of space-time itself. Future travelers might feel a faint echo of your presence, a chill of wrongness as they pass through the throat, never knowing they are walking through what was once a living mind. Then there is the most violent finale. Your entry, the additional mass and energy, could be the final straw that breaks the wormhole's delicate balance. The negative energy density fails, and the throat reacts like a snapped rubber band. The walls of the tunnel rush inward at impossible speed, crushing everything within into a single point of infinite density, a new singularity born from your passage. In this scenario, you do not traverse the cosmos, you become a tomb, your final act the creation of a gravitational grave that seals the shortcut forever. This is the core of the mystery, a gamble with reality itself. To step through is to accept that you may arrive as a pioneer, depart as starlight, live on as architecture, or die as a universe's final mistake. Perhaps the final destination is not a place, but a state of being. We have journeyed through 49 theories, from the mathematical birth of Einstein-Rosen bridges to the possibility of a conscious universe, but one grand, unifying idea remains. This final theory suggests that wormholes represent the ultimate evolutionary step for intelligence itself. A civilization that has mastered its planet, its star, and the energy of galaxies would eventually face a fundamental limitation, the sheer, silent vastness of space-time. The final frontier is not to conquer this emptiness with faster ships, but to reweave the fabric of the cosmos itself. Such a civilization would not simply use the universe, it would begin to architect it. Its ultimate project would be to transform the lonely, isolated islands of star systems into a single, interconnected network, a cosmic web of wormholes. This is not merely building a transportation system, it is a metamorphosis. The civilization would, in a very real sense, merge with the structure of reality, its consciousness and culture flowing through the tunnels it creates. The universe, once a dark and scattered collection of points, would become a single, vibrant entity, a living system with wormholes as its synapses, carrying thoughts and energies across the cosmic brain. In this view, the great silence we observe is not a sign of emptiness but a stage. We may be living in the quiet, early years of the cosmos before the first truly ancient intelligence begins this grand work, stitching the heavens together and turning the entire universe into a shared, conscious home. We have ventured from the solid ground of Einstein's equations to the wild frontiers where space-time, quantum mechanics, and even consciousness intertwine. These 50 theories are not just a catalogue of cosmic curiosities. They represent a fundamental human endeavor to understand the architecture of reality itself. Wormholes, while still firmly in the realm of theory, are far more than science fiction dreams. They are one of the most powerful tools physicists have for probing the deepest laws of the universe, forcing us to confront the limits of general relativity, the paradoxes of quantum information, and the very nature of time. Each idea, from the self-consistent loops of Novikov to the holographic wiring of the cosmos, is a different lens on the same magnificent mystery. So we leave you with a final question: which of these theories blew your mind the most? Do you have your own wormhole theory? Share your thoughts in the comments below. Make sure to subscribe for more journeys to the edge of science, and as always, keep